Hello, and welcome to the Malvern Panalytical Web Seminar Program. My name is Linda Bratica, and I'll be acting as host for today's meeting, which is entitled Improving the Development Efficiency of Drug-Encapsulated Nanoparticles Using Microfluidics and Multi-Angle Dynamic Light Scattering, presented to you by Dr. Pavel Abdulkin and Jake Austin. Dr. Abdulkin is the Head of Business Development for Dolomite and Particle Works, both of those being a black trace company. After completing his master's and PhD at Cambridge University, UK, Pavel went on to co-found several technology startups, including N4O, a company that specialized in the removal of liquid rocket fuel in mobile continuous flow reactors. Pavel is currently responsible for business development, and he is the head of business development of the Particle Works and Dolomite Microfluidics brands. Jake Austin received his master's in chemistry from the University of Reading, UK in 2016. He joined Malvern Panalytical as an applications development scientist and has previously worked for the company in 2014 as a year in the industry student. Jake has recently been working on Malvern Panalytical's newly launched flagship instrument, the Zetasizer Pro and Zetasizer Ultra, and has contributed to the development of unique features, including the multi-angle dynamic light scattering feature and particle concentration. So I thank these gentlemen for completing or creating this presentation for us, and thank you for taking the time to be with us. So I'm going to get Jake and Pavel on the line. Hello, gentlemen. How are you doing today?
We're good, thank you.
Very well, thank you. And good morning if you're joining us from Americas, and good afternoon if you are in Europe.
Right, good. So, Jake, could you give us a short little summary of what we're going to see today?
Yeah, so to start, basically, I'm going to talk about how Dolomite Microfluidics work with drug encapsulation, give an overview on the typical techniques that used to be used, batch encapsulation, and then moving on to how they've developed microfluidics and what that does. Then we'll move on to a brief overview of DLS and then into multi-angle dynamic light scattering, how that improves DLS, and then how that has improved the development work of Dolomite Microfluidics.
Well, great, thank you. I'm going to get the controls over to Jake.
Thank you.
Great, and you're set to begin.
Great, thank you, Linda. So I'll just give another overview over the presentation. So what we're talking about today, so a drug delivery solution is typically using encapsulation of drugs in a particle, such as PLGA or liposome nanoparticle. It's traditionally been done using batch methods to encapsulate the drugs. However, the drug requires to be reproducible and have a very narrow size distribution, so to be monodispersed. Batch methods, however, they actually have a lower level of control and is ideal and produces particles of broad distribution and low reproducibility. So an alternative method is to use microfluidic system, which uses a continuous flow rather than batch. The Dolomite Microfluidics provides a state-of-the-art automated continuous flow processing and droplet microfluidics. These ensure that the particle distributions are very narrow and monodispersed, and they have high batch-to-batch consistency. However, when developing these particles, to get them to the right size and to be narrowly distributed, they have to find the optimal settings to get to the target size. By using Zetasizer Ultra with multi-angle DLS, the iteration on this, finding optical settings, can be achieved much faster, and all the size populations that they have there can be characterized, saving them time and money on development costs. So I'm now going to pass over to Pavel, who will dive deeper into batch and microfluidics encapsulation.
Thank you, Jake. So fundamentally, what we want to talk about today is two techniques. One is droplet microfluidics, which enables fast and high-quality process for formation of nanoparticles and microparticles. The second is MADLS, which enables the analysis of these particles, and how the combination of these two techniques enables a very fast build, measure, learn cycle, which enables us, Particle Works and Dolomite Microfluidics, to iterate very quickly on our development and achieve spectacular results very quickly and very efficiently. So without further ado, let's dive straight in. So first of all, what is microfluidics And why should you care about it? You should care about it because it's a tool that enables formation of highly monodispersed particles. So fundamentally, we form emulsions if we're doing particle synthesis top to bottom, or if we're doing it bottom up, we're forming particles straight away. And we'll talk about this technique in a couple of slides. There's a number of ways in the industry to create emulsions or particles, but the extremes of these two techniques are the batch methodology. We have two miscible or immiscible liquids. You add one to another, you input some form of energy, whether it be agitation, whether it be sonication, whether it be heat, and create particles. The other extreme is the formation of particles in microfluidics, where you deal with microliter droplets or nanoliter droplets at any one time. You create them very quickly, and you create them individually. The biggest advantage of doing things using droplet microfluidics or continuous flow microfluidics is the ability to create highly monodispersed particles with CVs as low as 1% or below. The other really important advantage of this technique, which is sometimes even greater than the ability to create monodispersed and reproducible particles, is the ability to achieve very efficient encapsulation, sometimes in excess of 90%, and the ability to achieve this encapsulation with minimal input towards the particles. That means that if we're encapsulating fragile materials, such as complex proteins, we don't have to destroy them in order to encapsulate them. And of course, destroying them would reduce the point of the entire encapsulation process. So whenever we talk about making droplets in microfluidics, we talk about making them with love. And whenever we talk about making droplets in batch, we talk about making them with hate. How do microfluidic processes operate? Well, it's at droplet formation level. Fundamentally, what we're doing is we're crushing two liquids into each other very controllably, and these two liquids are immiscible. We are achieving our pumping using pressure pumps to create a very smooth flow at the point of the chip. And then we're simply imaging the chip directly, and we're adjusting relative flows to adjust the droplet size. So at first approximation, the droplets that we create are the size of the junction. So in this example, we see a 14 micron, that's 1/4 micron junction, making a range of particle sizes. So if I can find my laser pointer, then here, this is the optimal operation of the chip. And what we're doing here is we're creating 15 micron droplets in a 14 micron junction. So the size of the droplets is about the same size as the size of the junction. However, if I have a good emulsion stabilizer and I know what I'm doing, I can create smaller or larger droplets. So here, by increasing the relative flow rate of the continuous phase, I can decrease the size of the droplets to 1 micron. And here, by doing the opposite, decreasing the flow rate of the continuous phase, I can create droplets as large as 25 micron. Of course, in order to achieve these droplets, I need to start forming a droplet and close the droplet. Eventually, there comes a point where the material does not enable me to close the droplet fast enough. So when I increase the flow rate at infinitum, I will get to a point called the jetting limit, where I'm no longer making my droplets, I'm making a jet. And typically, we would operate our chips at 10% below that, so that we can get stable formation over periods exceeding 24 hours. Another method of forming particles in continuous flow is nucleation and growth. So here, the fundamental difference is we're no longer dealing with immiscible liquids, we're now dealing with two liquids which are miscible. And we're not forming a droplet and then shrinking it down to form a particle, we're growing particles from individual strands upwards. So we would typically use materials such as acetone to dissolve a polymer, and these would be miscible with water. And water will act as an anti-solvent. So our polymer with API would be flowing down this end through the central channel where our droplet phase would normally go, and our anti-solvent would go on the opposite ends of this. This will enable us to create a sheaf where we are crushing individual strands of the polymer out, and as the two liquids mix, these strands grow. The greatest advantage of doing this in continuous flow is that this process is highly controllable. what happens from the point of view of individual particle is that you nucleate a strand, and that strand grows by combining with other strands, and then eventually it gets to the point of irreversible growth and continues to grow. We stabilize this against irreversible growth or large aggregation by adding emulsion stabilizers or surfactants. Now, if you're doing this process in batch, the variability of conditions across a batch reactor is very large. And so individual strands of polymer would be exposed to different conditions, whether it will be concentration gradients, temperature gradients, or simply residence time differences as the solutions take time to mix, as the solutions take time to find their way in and out of the reactor. None of that is a problem with a continuous flow system, because the individual channels are often order of 100 or 50 microns in size, and so temperature transfer coefficients, heat transfer coefficients, and mass transfer coefficients enable us to make sure each individual strand experiences the same set of conditions as the other, which means that all of the particles, when they come out of the reactor, have had exactly the same set of conditions and are therefore pretty much exactly the same size. Now, we can control the size of the particles by adjusting all the same levers that chemists are used to pulling on in their standard laboratory practices. We can adjust residence time by changing either the size or the dimensions of the chip or the flow rate through the chip. We can obviously adjust the temperature at which the chip sits. We can adjust the relative flow rates of the continuous and droplet phase. And we can do this very quickly and very controllably. And so we can achieve particles of a variety of sizes depending on the system. And as I will show you later, we can have particles as small as 40 nanometers or as large as 800 nanometers produced by this system in a highly controlled environment. So let's just reiterate what this looks like in batch and what this looks like in flow. So in batch, if I want to encapsulate my API, I would typically have two immiscible solvents or two miscible ones that I have to add to each other very quickly. What this means is I will have to create a range of conditions, and the variation of the range of conditions will be proportional to the size of the vessel. The bigger my vessel, the bigger my problem. I will then have to, as a consequence, I will have to create a set of particles which some of them will have large concentrations of the drug in them, some of them will have low concentrations of the drug in them. If I'm creating an emulsion, I will have a variety of droplet sizes, and again, some will be highly loaded, some will be poorly loaded. I will then have to dry these particles out, and with that, I will have to remove some of my API. Some of that API would not have had the chance to find its way into the particles in the first place. Now, all of this means that my reaction process takes a lot of time, typically 3 to 5 hours, that my results are non-reproducible, and that my encapsulation efficiency is 5 to 20%. Now, that's a big problem if I'm working in the pharmaceutical industry, because the value of individual droplets is very high. And if I have to lose 95 to 80% of it, that is a big problem. Now, the opposite of this is encapsulation using, microencapsulation using continuous flow or droplet microfluidics. Here, we've got direct control over the particles as they form. The reaction time is 2 to 10 minutes, and sometimes we can achieve the same results in 30 seconds. The encapsulation efficiency is 80 to 95%, so my waste is very low. And of course, the reproducibility is fantastic. So if I do an experiment on Tuesday and then do an experiment on Friday, I can be sure that the results are exactly the same. And as you can see from this picture in the bottom left corner, what this shows you is a real image of the particles forming on the side of the sheath, and we can control our conditions to form 40, 100, and 800 nanometer particles, or anywhere in between those, very controllably. On the other side of the size spectrum, when I'm trying to create larger beads, I just want to show you a few examples of the unique materials that you can create using microfluidics. So you can obviously encapsulate materials in PLGA or liposomes in batch, and as we've shown before, the big problem with this is efficiency. But also, you need to create unique materials for drug encapsulation. So if you look at the left-hand side of images, these three, what we're doing here is we're creating beads, 5-micron beads of PLGA particles. Now, APIs that our customers typically want to work with are water-soluble, i.e. hydrophilic. PLGA, by its nature, is hydrophobic. And so it goes into solvents such as dichloromethane. Now, if I wanted to substantially enhance the efficiency of my drug encapsulation, and I wanted to encapsulate powdered API into a bead, then that process is impossible in batch, because I will have to put my API into water and my PLGA into the oil phase, and when I mix the two, my API will end up in water, my PLGA will end up in the oil phase, but no drug will end up in the PLGA. In microfluidics, because we control the streams precisely, what we can do is create a suspension of a finely micronized API inside the oil phase, pinch that off in our device, and create those beads with a powdered API still inside of it. And because surface tension takes care of things, the encapsulation efficiency is nearly 100%. And these beads are highly efficient at release, as the degradation of the bead results in the release and solubilization of the powdered API. Now, in other cases, we want to achieve a slightly different release profile, where we want to encapsulate our API in solubilized form into water droplets. So we'd form these droplets of water inside droplets of the PLGA. And when they dry, these will start looking like raspberries. So these tiny water droplets, and they're surrounded by a shell of a polymer matrix. And in the fluorescence microscopy image here, you can see API fluorescent in red and the PLGA fluorescent in blue, and you can see clear separation between the two. Now, this release profile is very different. What happens is the PLGA starts to degrade back, and that pops the water droplets open, so you get spiked release each single time this water droplet is released. And that's very important for some of the applications that we work with. Now, so as you can see from the previous slides, we work with microparticles, we work with nanoparticles, and all of this goes towards encapsulation of API and drugs in PLGA and liposomal particles. Now, before we got the chance to work with MADLS techniques, we could only analyze our particles by standard DLS, which did not create sufficient resolution. The problem with standard DLS instruments is that they will only show us an average of the particle size in our sample. In other words, if we have particles of 40 nanometers in size and particles of 300 nanometers in size, the instrument will show us an average, and because it's based on intensity scattering, it would bias that average towards the larger size. So in my example of 40 and 300 nanometer particles, we might get an average of 200 nanometer particles. Whereas the reality is 200 nanometers is exactly the size we don't have in that sample. And so previously, we would have to rely on a variety of techniques to characterize our particle size. So we would do transmission electron microscopy, where we could image our particles directly using an electron beam. We could do scanning electron microscopy or atomic force microscopy. Now, these techniques enable you to get a tiny glimpse onto your sample. You'll see the particles directly, and that's great. However, you are looking at a portion of a grid which you had to preload. And on that grid, particles can be distributed relatively randomly, and the larger particles tend to go to the outside. Now, what that means is you have to spend a lot of time convincing yourself that you are, in fact, looking at the representative sample. So you could, in my example of 40 and 300 nanometer particles, be only looking at 40 nanometer particles because your 300 nanometer particles are hidden from you on the outskirts of the grid. The other set of problems with this technique is with all of these techniques is that they're time consuming. So with transmission electron microscopy, SEM or AFM, you can typically achieve a throughput of 5 to 10 samples a day, and that will require a very skilled microscopist. And also, obviously, these techniques are destructive as you're shining an electron beam at a sample, and particularly in the case of polymeric liposomal particles, it is very hard to actually distinguish the particles there. Now, there are other techniques which can enable you to look at particle size distribution as a general aggregate. And these techniques include things like powdered XRD diffraction, whereby looking at the peaks available to you, or more specifically the width of the peaks available to you, you can judge the particle size, the average particle size for the entire sample. And you can have various thermogravimetric analysis and colorimetric analysis, which also correspond to particle sizes. In order to determine an average and accurate particle size, a good scientist will have to undertake both of these techniques to convince themselves that the sample that they're looking at is indeed the sample of the thing they're looking at. And this analysis will take days, if not weeks. Now, over to Jake to explain some of the finer details of the MADLS instrument.
Thank you, Pavel. So I'll just give a brief overview of dynamic light scattering for those who aren't familiar with it. So DLS is used to measure particle size. Essentially, this is based on the diffusion speed of particles under Brownian motion. So we can measure the size of a wide range of samples and materials such as polymers, gold nanoparticles, inks, liposomes. And these will be dispersed in a medium such as water and placed into a cuvette. We then put this cuvette in front of a laser, and the particles inside that cuvette will then scatter the light. We then collect this light, the photons, in a photon counting device, and we count how many there are. When we plot this over time, so the number of photons will fluctuate up and down, and these fluctuations correspond to the speed of the particles. So what we do is we correlate the fluctuations, so compare the fluctuations against time, and we get this curve here. And then after we have a correlation function, we can then apply our algorithm and get either a size distribution or a size average. As Pavel mentioned, an issue with DLS, though, is the lower size resolution compared to other techniques such as TEM. So when you perform a DLS measurement, all the scattered light is typically detected at one angle. So either from backscatter, so about 173 degrees, side scatter, 90 degrees, or the forward direction at 13 degrees. So an example here is when a single angle measurement, in this case backscatter, was used to measure an early development PLGA nanoparticle sample. The main peak was made up of only one population. So at this point, using DLS, you don't really know, because it's so broad, if what that sample actually, or this size distribution actually represents in your sample. However, the Zetasizer Ultra has a unique capability, which is multi-angle dynamic light scattering, or MADLS. So when we use MADLS to measure the same sample, two populations are resolved, one on the left about 200 or so and one about 700. So MADLS utilizes all of the angles available in the Zetasizer Ultra, so that's back, 90 and forward scatter, providing higher resolution, ensuring that your distinct populations are correctly characterized. So how we do this is we take a measurement at each angle, just like we would in single angle DLS, but instead we have three correlation functions this time. We then apply, rather than a normal size algorithm, our MADLS algorithm to all three to find a particle size distribution that fits all three of these correlation functions. So then looking at how MADLS has improved the development efficiency. So by measuring the sample with MADLS, as we've seen, distinct populations can quickly be found. So it takes only a few minutes to get a MADLS measurement. Otherwise, a sample may need to be measured on a different technique. It's more expensive and time-consuming, such as transmission electron microscopy. And once these peaks have been identified, the methodology used to produce them can be adjusted. For example, the flow rate, as Pavel's already mentioned. These particles can be resynthesized and immediately put back on the Zetasizer Ultra, investigating exactly what we've got there, until we get to the point where we have just one peak, which we know, because we can't resolve anything else, is our monodispersed particles. This allows the particles then to meet required specifications much earlier, a much quicker iteration at a lower cost than if we weren't using MADLS, because that would require using multiple techniques, or potentially ones that destroy the samples. Now pass back to Pavel.
Thank you, Jake. So all I wanted to do here is to demonstrate how our group uses this on an everyday basis. And you're going to see a few pictures of my good friend and colleague Ben Nuttett. He's our head of chemistry. He runs our custom development group. He's responsible for taking care of our customers and taking them through the journey of just starting off with microfluidics all the way up to scale up through their R&D. Now, Ben is responsible for a group of about 5 scientists who are very happy to help you with your nanoparticle and microparticle development in microfluidics. Now, let's just show you an episode of 24, so to speak. And we've got Ben here on a Monday morning, and he's analyzing his results, and he's creating trend lines, and he decides that he wants to do 5 or 10 experiments to determine how pulling on various levers, such as adjusting residence time or temperature will affect the particle size. And Ben lives 10 years ago, and he has to do this using batch chemistry and standard analytical techniques. Okay, so it's Monday, 9:30 a.m. Ben analyzes his samples with his morning coffee, and then by 10 o'clock he goes to the lab. By 10:40 a.m. he can start making up his samples, and he's starting his reagent preparation. By about 11:15, he finally gets a chance to get his batch vessel, and he's starting to prepare his solvents, his reagents, and starts pouring them in. And by noon, he sets his experiment going, and the experiment takes 3 hours, so by 3 p.m., he's ready to start collecting his first sample. He can parallelize this process out, so he can have 5 batch vessels running in parallel, and so by the end of the day, he's then got 5 samples that he's ready to put onto TEM or SEM grids. So by 4 o'clock, he's loading up his samples onto SEM grids, he's processed them, he's diluted them sufficiently, and now he's ready to load. It's 4 o'clock on a Monday afternoon. And once he's loaded them, it's the end of the working day, and he has to go back home. Now, we are a company of 150 people. We don't have TEM or SEM on site. However, we are lucky enough to be based next to both Cambridge universities, that's Boston and Cambridge, UK. And so we get to work with some of the finest academics in the world and use some of the best analytical techniques there, such as TEM and SEM. Unfortunately, they're not available on every day, so we have to book them. So the first slot that Ben is able to get on this particular week is a Thursday slot. Happens to be a very good week. So on Thursday, he has to travel from our site to Cambridge University. So by 10:30 a.m., Ben's in Cambridge, and he's ready to start loading his samples into, well, in this case, a TEM instrument. He has to pump samples down to achieve high vacuum. So he has to use liquid nitrogen traps, which is exciting, but time-consuming. So by noon this time, he's got his first sample loaded, and it takes him about an hour to reload every single sample. So by 5 p.m. on Thursday, he's analyzed 5 samples that he synthesized on Monday. He then has to travel back to the office, and by 6 p.m., he's tired, he's unhappy, he's having his evening cup of tea, and he's trying to think of what to do with his results. Now, let's have a look at how the situation changes when we introduce the combination of microfluidics and MADLS. Okay? So on Monday at 9:30, Ben analyzes his trends, goes to the lab at 10 a.m., starts his microfluidic system going at 10:30. At 10:45, he's got his first sample loaded, and by noon, he's got 5 samples analyzed, and he can have his coffee in the office, very happy, and now with a muffin. Now, that might be funny, but the reality is that the combination of microfluidics and MADLS enabled us to create a very quick build, measure, learn cycle, which enables us to go through up to 40 samples a day and iterate very quickly on our R&D. That means that we can achieve results very quickly and very cost effectively. And the reality of this means is we have very quickly become leaders in microencapsulation of API within PLJ and liposomic systems.
Now, to give a final summary of what we've gone through today, so we said about how microfluidics drug encapsulation can be used to create nanoparticles, which provide better monodispersity, increased encapsulation efficiency, and improve reproducibility than a batch system would. And then by combining microfluidics with the Zetasizer Ultra and MADLS, the characterization of these particles is much easier and faster. It's giving you quicker iteration on your work cycle and more consistent production of nanoparticles at a lower cost. And thank you for listening. Now to pass back over to Linda.
Thank you so much, gentlemen. A great presentation. And now we're going to open up our question and answer session. And we do have our principal scientist here, Dr. Kevin Madison, to assist us with this. And Kevin Madison completed his doctorate from Purdue University in 1999. And in 2002, he joined Malvern, now Malvern Panalytical, where he served as many things and is now principal scientist and heading up the pharmaceutics and food group. So thank you for being with us, Kevin.
Thank you for that promotion.
Well, you are who you are, and I have known you for, I think, 19 years.
It's been a while.
And it's nice for us to be able to help all of you, our attendees, get your answers to your questions. So we've got several questions that have already come in. And Kevin, I'm going to let you take this away. I'll get to our first one here.
All right. Nice talk, Pavel, Jake. Very enlightening. Appreciate your time and efforts. I do have a couple of questions here. Well, 5 at this point. The first one comes from me, and I apologize. I'm a bit of a novice on the drug encapsulation side of things. But, Pavel, this one's for you. How are you measuring encapsulation efficiency, just kind of for my own education? How are you getting that information?
It's a fantastic question. It depends on the API or the drug. We did deliberately say drug as opposed to active pharmaceutical ingredient, as about 70% of our work is with API and pharmaceutical companies, and about 30 is with companies wanting to do all sorts of things, including CBD and THC encapsulation. Now, how do you measure encapsulation efficiency? There's a variety of techniques you can use. Basically, all you need to do is measure the concentration of the drug in the prior to encapsulation, and then in your either in your particles or within the continuous phase after the encapsulation. And as you know, you can use multitudes of techniques from HPLC and simply measuring the concentrations, all the way up to, say, fluorescence microscopy, where if the drug fluoresces, such as in the case of doxorubicin, which is a standard drug for breast cancer therapy, it fluoresces green, so the images you saw of the micronized API encapsulating glowing green, that's doxorubicin. You can simply look at the intensity scattering profile of the bead compared to the background. And then if you combine
so you know what you put in, you measure what you put in, and then you wash out and measure what's left, and that's how you're getting encapsulation. Just
exactly. You know what you had at the start.
Yeah.
Exactly. You know what you had at the start. You know what you had in the end, and the ratio of the two gives you your encapsulation efficiency.
I got you. All right. Here's one from the audience. This had to do with the early part of your talk, when you were talking about the efficiency of the microflow technique. So one of the audience questions was, what are essentially the particle size limits for the microflow technique versus batch emulsion technique?
Right. So it's hard to give you exact numbers because that depends on the specific system that you're working with. At first approximation, whether it's PLGA or liposomal, and then as you dive deeper, what molecular weight of PLGA strands are you working with? What emulsion stabilizer are you working with? Now, in my experience, what you can do with microfluidics is about 40-30 nanometers in flow. Now, the interesting part about microfluidics, which is very important to some of our customers, is you can make these particles unprotected. That means they don't have an emulsion stabilizer or surfactant on the surface as they go through the chip, and then when you collect them, you coat them against agglomeration. Now, when you do this in batch, your particle size variation tends to increase, and so to about 100%, 50%, and you can generally, you might be able to achieve the same particle size in absolute terms with greater variation, so 40 nanometers on the lower end and 800 nanometers on the upper end, but your particle size will be more polydispersed, and critically, in the case of PLGA, you will have PLGA or an emulsion stabilizer hybrid, so you'd have to incorporate PVA into your PLGA particles, and that makes the release unpredictable. Obviously,
I got you.
You've got an added issue of not knowing how much API is inside each individual particle.
Now, do you see that increased polydispersity at both ends of that size range, the lower limit and the upper limit?
Absolutely. It continues to scale. It tends to be worse at the smaller scale.
Gotcha. Another question from the audience has to do are on the same subject. Does this work fine with double emulsions, or is it really pretty much tailored to single emulsions?
No, so you saw one of the images I had multiple emulsions, where we had multiple water droplets on the inside, and you can use exactly the same technique to create double emulsions. In fact, 80% of our efforts and customer work at the moment are in double emulsions. So we do that quite routinely.
Okay. All right, staying with you, Pavel. The MADLS technique facilitates a calculation of the particle concentration. Are you using MADLS to extract a concentration, or at this point you're just doing size measurements with it?
So most of our lab work it is critical for us to get size measurements, and more importantly, to get the idea of size distribution. So that's 90% of what we use MADLS for. And actually, I'm very pleased to report that we haven't used TEM or SEM for the last 2 years. So this build, measure, learn cycle has really worked for us very well. So 90% of what we do is we're getting the size, but you can use MADLS to estimate the concentration of the particles. I'd like to hand over to Jake at this point to give you just a few more details on that.
Yeah, so to measure the particle concentration, we basically take the scattering that we get from the MADLS measurement, and we, using the refractive index properties of the particles that are input by the user, we can estimate how much each particle should scatter at that size, and then we basically divide the total number of scattering by how much each particle should scatter, and then we can convert that into particles per mil measurement. And that gives us reasonable accuracy. We expect to be below 40%, often can be below 20%. It depends on the particle size and how repeatable the measurements are. And we typically see that as more of a screening tool for concentration.
How monodispersed, Jake, do the samples need to be for that MADLS concentration transform?
That's a good question. I think I'll have to get back to you on that with an answer. So it's better with a monodispersed sample, so one peak, but it is possible to have multiple peaks. We give a particle concentration for each population. But
right, that's multimodal. That wasn't the gist of the question. The peak, the individual peak itself. Can you have multiple unresolved populations within a single peak and still get valid concentration measurements?
It won't give you an accurate one because in that case it will be too broad. So because we use essentially the peak size, so the average for that peak, if you've got a very broad one, it will be inaccurate, but you can use it as a relative measure to compare against other samples, or if you're changing your process to see what difference it makes.
All right, that's the answer we were looking for. All right, hold on a second here. We've got another question that stood out as a really good one.
This one here, the bottom one?
No, the one about integrating the measurement into the microfluidic device itself. All right, I'm going to read this straight off the screen. Can you do DLS on particles within the fluidic device in situ?
Can I just say,
nobody said this was going to be easy, Jake.
Yes.
Yeah, so essentially no, but it's something that we can look at in the future, but not currently.
Okay. Another question here from the audience. What is the typical throughput of the microfluidics system, for example, considering 100 nanometer particles or 500 nanometer particles?
That is an excellent question.
Pavel, I believe that question is probably over to you.
No, I think that one's for Jake. No, so excellent question. I didn't pay anybody to ask it, which is great. So we've got a range of systems that work at a range of scales, obviously. So we have laboratory-sized systems, and they will typically throughput 30 grams of the material a day. So this is what we call R&D systems, small scale. We've got larger systems that we call telos that work by multiplexing microfluidics. And that typically has about 100 junctions in it, working simultaneously at any one time. Now, that system has a throughput of 3 to 5 kilograms a day. And then you scale up further. We are currently working on industrial systems, which are capable of throughput of 50 kilograms a day. And we're looking to get to the scale of tons per day.
Okay.
So
I have one more. a little bit tangential, but this has to do with your TEM measurements, Pavel. For lipid nanoparticles, how are you avoiding destroying the structure under vacuum when you're doing TEM measurements?
Very good question, and it's got two parts to it. So if we're looking at size, then what you would typically have to do is you would have to sputter your particles in materials such as gold, and then you would do SEM on them or AFM on them. The structure question is even more intriguing because if you look at the liposomes that are currently being used in the industry, the 99% of them, you don't actually know if it's a lipid particle or a full liposome. And to determine whether you have a complex, true bilayer liposome requires very expensive analysis, so most people don't do that.
Okay. That's all we've got. Linda, you want to wrap this up? Thank you very much, guys. Nice presentation.
Thank you.
Thank you. Yes, and back to our attendees. Thank you so much for being with us and taking the time. And now I'd like to hand back to you, Jake and Pavel, to close.
Thank you, Linda. Just like to say, hope that you've enjoyed our presentation today and that you've learned about the benefits of microfluidics and how much a help it is in generating your nanoparticles, exactly how you want them to be, and how the Zetasizer Ultra is an ideal fit for it as well to characterize them. Thanks again, everyone.
Thank you all very much for listening. I'd just like to emphasize in closing that the combination of microfluidics and Zetasizer Ultra, in this case, enables a very fast build, measure, learn cycle, and to us, that completely revolutionized our R&D profile. Now, I'd also like to add, I know I've been very flattering about Malvern Instruments on this webinar, and well, that's
I was going to ask if you had a check in the mail.
Not yet. I'm expecting one. But what I did want to emphasize is we were very skeptical about the instrument, and we have used other DLS instruments before, and they just didn't give us the results we wanted. And when Malvern approached us about this project, we wanted to give it a try, but we were very skeptical about the results. And we're very happy to be proven wrong, and we're very happy to be using the instrument in our lab on a daily basis.
Well, thank you for those kudos.
Yes. Thank you, Pavel, so much again, and good day to all. Goodbye.